And welcome back, everybody. Okay, so Houston, we have a problem. Problem 2. This is Physics 150 discussions on YouTube. This is Selman speaking. Here we have a problem in which we have a segment of wire shown in the picture, and we want to compute the magnetic field at the point P. Now, there are 3 sections to this thing, and what we're going to do, just to give you a preview of the problem, is find the magnetic field for each segment and then add them up to find the total magnetic field at the point P. Now, one of the techniques that we're going to use to do this is you always want to use in your favor the fact that you have the freedom to choose your coordinates however you want, which means that you might as well, and of course, you do want to set coordinates on this thing because that's going to be, we're going to want to solve this using the law of Biot-Savart. So we'll get to that. We'll write it down. It involves a cross product. And because it involves a cross product, you're going to want to write out your coordinate system so that you can write your vectors in component notation and then go on and compute your cross product. So what's going to be useful is to, as you can see, I've drawn out that picture right here. And you're going to want to align one of those long straight segments with one of your axes. That's just going to make life much easier for you to compute some of these things. Okay, so in general, how do we compute the magnetic field? There are 2 ways. There's the law of Biot-Savart, and there is the Ampere's law. But here, we want to use the law of Biot-Savart. And in general, what it looks like is the following. And so this is going to be in analogy with how we use the infinitesimal form of Coulomb's law to generate the magnetic field for an entire source. We're going to do a similar thing with the law of Biot-Savart. You take a little increment of magnetic field is going to be created by, so mu naught over 4 pi, those are the prefixes, times the current in that segment. And then dl cross r hat over r squared. Now, what is r hat? R hat is the unit vector that points from the segment of wire that contains the current to the point that we're interested in observing the magnetic field, in this case, the point P. R is the distance from the current source to the point P, and dl is the direction of the wire segment that we're interested in. So we're going to see how this all comes about in the problem at hand. So let's break this problem into 3 parts like I was mentioning. Let's call this first segment here 1, this bent curved piece 2, and then this other long straight piece 3. So let's get started, and we're going to see how we use the law of Biot-Savart in practice. So just looking at part 1, what we're going to want to do is actually write down all of the vectors that we're interested in. So the vector r points from, so actually let me draw the picture just so we can see what we're talking about. So take a little wire segment, dl, to be along the direction of the current. So it's going down like this. This is dl. And then the vector r points from that infinitesimal wire segment all the way to the point P. So you have got a vector r which points from that little infinitesimal wire segment to the point P, and that's the vector r. Here we can see that they're both vertically downwards. I chose my coordinates so that this particular part of the problem could be very easy. Everything's just in the vertical direction. So we can write out the r vector is going to be some distance r. Now this is variable because the actual wire is very long in the y direction. So there's various different values for r that we have to integrate over in principle. And this is going to be in the minus y direction. The unit vector is just in the minus y direction. So in this case, r hat is just equal to minus y hat. Here we're using x hat, y hat, and z hat for the x, y, z unit vectors. Okay, dl, now dl was also in the minus direction, so it's minus some amount dl in the y hat direction. And so when we set up our law of Biot-Savart, so d, the increment along the first segment, is going to be mu naught I over 4 pi. Okay, this part stays the same for most of these formulas. And then you've got dl cross r over r squared. Now, in order to compute this, what we really need to do is compute dl cross r hat. Oops, so I made a mistake there. That's fine. But it is important to maintain the distinction between your r vectors and r hats. Our unit vectors have magnitude 1. So just going ahead and computing this cross product, we have minus dl, the y hat direction, crossed with minus y hat. This is equal to positive dl y hat cross y hat. And at this point, we've done a few cross products, so we know that this is actually equal to 0. So this is equal to 0. And technically, dl has units of meters, so this is 0 meters. Unit vectors, of course, have no units at all. Okay, so what that implies is that that entire thing, dB1, is equal to 0 Tesla. Beautiful. Therefore, of course, if you add up over all such little increments and they all give 0, then you get 0 magnetic field from the first contribution. Now, let's actually skip to the third piece, because the third piece is going to be very similar as well. Remember, with the first piece, the reason that this ended up actually giving a vanishing result is because r vector and dl are in the same exact direction. Now let's look at the third segment. In the third segment, the current is going to the right, so you take a little segment and it's going like this, dl. And then then the r vector that points is in this direction. This is r vector. We could call it 3 just to be clear. And while they're not parallel in this case, they're anti-parallel. They're 180 degrees apart. And that actually will still give you a cross product that's 0. So let's go ahead and look at this really quickly. So say that I was doing the second piece and I wanted to do it the full justice it deserves by the third piece, rather. This is mu naught I over 4 pi dl cross r3 over r squared. Okay, in this case, say that, and again, I messed up with my r vector versus unit vector. Okay, this is a unit vector. Now, say that my unit vector is just some r hat, which I have there. Then dl, we know it's in the opposite direction to that. So dl is going to be equal to some amount in the minus r hat direction. So actually, let's give myself some room. Or rather, that's fine. We just do, this is dl in the minus r hat direction. So now let's compute that cross product. This may be obvious for many of you, but let's just actually just go through and do it. So when I do DL crossed with R3 hat, then what I have is DL minus DL R3 hat crossed with R3 hat. Okay, and what you get is minus DL R3 hat crossed with R3 hat. And I know that we use this property for, say, x hat cross x hat is equal to 0, so on and so forth. But this is just true for any vector. If you cross product a vector with another vector that's parallel to it, it is 0. It's not just although this is also true for x hat and x hat, or y hat and y hat. You could set some weird vector like, for example, this is completely random, but you could, if you had some vector A that was like 3x hat plus 4 y hat, and then some vector B, which is pretty much the same as that, except it changes by a multiple, like 6x hat plus 8y hat. Well, then this vector is just equal to 2 times the other one. It's 2 times a hat. And when you take the cross product of these things, they are going to give 0. So A cross B, and you can check this for yourself, that's going to equal 0. That's just me showing to you that as long as the vectors are proportional to each other by a constant, they are just their cross products give 0. So what that ends up meaning is that the third contribution is also equal to 0 Tesla. Perfect. So that just leaves us with the second segment. So let's take a look at that real quick. The second segment is going to be this curved segment that you see in the middle. And so we're going to want to be a little bit careful about how we set things up. So let me redraw the picture so we have a little bit more room. So this is for segment 2. And let's draw it big. Okay. And I'm not going to draw all the other bells and whistles because we're only interested in this curved segment where the current is flowing from left to right. This angle right here is theta. This is a fixed parameter and it's given in the problem. So this is not a theta variable. What we are going to want to do is, and this is x and this is y, what we are going to want to do is set up a new variable called phi. Phi is often the other name that we use for an angle. Of course, this distance here is still r. And phi in this case is going to be the angle, because what we're going to want to do is consider a line segment from such a line segment like that. Consider the magnetic field from it at the point P, and then add up over all such. So we need a parameter that's varying. And the distance away is actually not varying, if you can see that, because this is a segment of a circle. And of course we know that all points on a circle are equidistant from its center. So these are all a distance r away. What's changing here is the angle phi as we go from left to right. So now let us think about how we can write down these vectors. So we want to write the r vector, which points from, so the r vector is going to point from a point on the circle to the center. So one way to write this is minus r, so r is the distance, so it makes sense that r shows up in the r hat direction. Now, what is the r hat direction? So the r hat direction, and I'm just going to write this out, and you can see that it kind of works. Actually, let me give myself some more room. We're going to see that this, in fact, makes some amount of sense. So the r hat direction is going to be minus sine phi in the x hat direction plus cosine phi in the y hat direction. Now, let's think about this. And we are going to use the example of when phi is equal to 0. This is the point at which phi is, the vector is aligned with the y-axis. So phi equals to 0 is right here. So let me use another color. This is the point right here. That's phi equals 0 degrees. So at that point, we would expect the r vector to point from that top point of the circle down to here. We expect r to go like this. So it should have no x component, but only a y component. But for example, here, we expect it to still be negative, for example. That's also r. We expect it to have, and you can see here that it's going, this vector r at this point on the other end of the segment is going to go to the left and down, so that explains the negative. And you can prove to yourself that actually the way that I wrote it is exactly what you want for this unit vector. So it works for phi equals 0, and you can actually see that it does work for, and it is also a unit vector because when you dot it with itself, it gives 1. So it's got all the properties that we want it to have. So that is our r unit vector. Now let's go ahead and look at what is dl going to be. Now dl is an infinitesimal segment that is tangent. When the wire segment is curved, dl points tangent to the curve. So when you have a circle, that tangent actually is perpendicular to the radial vector. You guys remember this from the first semester of physics. When you have a particle in circular motion, its velocity is tangent to the circle, and that's perpendicular to the acceleration, which is in the direction of the radial vector. So this is something that we're actually familiar with. If you want, you can use an analogy like the current is due to electrons that are going around a circular segment. So the current at that point is tangent to the circular segment. So you can do something like that. Here r hat would be in that direction. Actually, and what you're actually going to see is that dl and r hat are perpendicular to each other. But first, let's actually write out a specific form for what dl is. And we're gonna check this for the easy case of phi equals 0 in a second. So dl, I'm going to write something out here and see if you agree with it. We want to choose dl. Choose dl such that it is perpendicular. It is perpendicular to r hat, because we know that it should be. So, but just looking at r hat, it's not necessarily obvious what is going to be the vector that points perpendicular to this. And the way to actually enforce this is that you require, and this is how you pick, construct certain vectors. you require dl dotted with r hat to be equal to 0. Remember, you have something like x hat dot y hat equals 0. Anytime you have a dot product equal to 0, it means that those two vectors are orthogonal or perpendicular to each other. So requiring this is the requirement that these vectors are perpendicular to each other. And I'm going to skip the steps, but it's actually a good exercise for a lot of you to figure out how to do this. You can actually show that if that's the case, with that requirement, up to an overall constant, you can actually get dl has got to be equal to some infinitesimal length, dl, which is a scalar, not a vector this time, times cosine of phi in the x hat direction minus sine of phi in the y hat direction. Now let's go back and look up at this picture. At the top, we see very clearly that for this to be tangent right here, it's going to have to go to the right, and r hat is going to have to go down. So let's just check that our work makes sense for the situation of phi equals 0. So at phi equals 0, what we have is that r hat is equal to minus y hat, and that dl vector is equal to some infinitesimal length. And cosine of phi is 1, sine of phi is 0. So this is just dl in the x hat direction, which is exactly corresponds to the picture that we had. And if you computed dl cross r hat because we wanted to compute the law of Biot-Savart, then what you would get is, in this one specific case, we're actually going to do it out more generally because I think that that's a good exercise. We are going to do dl x hat crossed with minus y hat. This is minus dl x cross y. X cross y, you astute viewers will remember, is just z hat. So this is minus dl in the z hat direction. Okay, so let's now go back to the law of Biot-Savart. Let's just write it out for a second. So this is dB2. If we want to compute the magnetic field at the point P, we need to compute this. Mu naught I over 4 pi. And this is dl cross r hat over. And what is the magnitude of r? Now it's just the radius. So this is over r squared. So that's just a constant. Now let's compute what dl cross r is in general. dl cross r hat is equal to, so dl was, remember, dl times cosine phi x hat minus sine phi y hat cross. Again, I'm being very general here because I actually think that it's useful for you guys to see a computation done out in a little bit more generality like this. I think that Jesse's solutions on Blackboard are very good and they're very concise and they give you a lot of physical intuition, but sometimes students just want to see why it is, how I could have gotten there in a systematic process. And so this is just what I'm trying to afford you guys. Just sort of color in and flesh out what's going on there. And then when I do the r hat, I have a minus sine phi in the x hat direction plus cosine phi in the y hat direction. Now I'm gonna have to FOIL all of this out, so this is gonna get messy for a second here. Let's factor out the pieces that we can, which is the dl and the minus. So minus dl. Let's open our brackets right here. So when I do this product, this cross product, I'm going to FOIL essentially, so I'm going to multiply the first term by the first term here, and then by the second term there. And then I'm also going to then multiply this term by this one, and add all those up, making sure to keep the orders correct for each. So what I get is cos phi sine phi x hat cross x hat for the first term. And then you're going to get this second red line is cos phi times cos phi. So you're going to get plus cos squared phi x hat cross y hat. Plus you're going to get another term that looks like you have, this is going to be, when I do it the other way, it's going to be minus sine squared phi y hat cross x hat, and then I believe minus cos phi sine phi y hat cross y hat. Okay, now we're all mature adults here, so we know that this is equal to 0, and this one is equal to 0. Very good. One that is a little bit less obvious, but hopefully still we know it at this point, is that y hat cross x hat is equal to negative x hat cross y hat, and that this is equal to, which is minus z hat. And of course, x hat cross y hat is z hat. So actually you can condense a lot of this, and we have that dl cross r hat is going to be minus dl cos squared phi plus sine squared phi in the z hat direction. Of course, this is a trig identity. This is equal to 1. And so what you have is that dl cross r hat is equal to minus dl in the z hat direction. Very, very good. So we're getting close to where we want to be. So you've got db2 is equal to, okay, so actually let me include those minus signs everywhere. So this is minus mu naught I over 4 pi r squared, and now this is dl in the z hat direction. So we're almost there. If we just look back at the picture that we had, now we just want to integrate along all of those segments of that curved wire. So from phi equals 0 to phi equals theta. And the way to do that is to remember that we're dealing with a dl that comes from a segment of a wire, or of a circular piece of wire. So this is some side work. Recall, you've got some circular piece of wire. This is some distance r. And some segment of this circular wire, S, is equal to that radius times the angle that's been elapsed. So I'm using theta here in a different context. I apologize for that. It's old habits die hard. But the point is that if you want a very small segment of the wire, then that corresponds to a very small segment of angle. So what you have is that dl is itself r times actually d phi in our case. Sorry for the confusion with the variables. So that you've got db is equal to mu naught I. Now there's an r coming from the dl over 4 pi r squared. Now you've got a d phi and a z hat. So you get one of these r's canceling out with one of these. So I can actually write this out so that this is mu naught I over 4 pi times r d phi in the z direction. Now we want to integrate this thing. And we're going to integrate, so to get this, you're going to integrate that whole thing from phi equals 0. So this is from phi equals 0, which is at the top of the circle, to phi equals theta, which is at the bottom of the segment. And this is mu naught I d phi over 4 pi r in the z hat direction. So, excuse me. So we can pull all of these factors out. This is mu naught I over 4 pi r. And this is the integral from, I guess, or did I do this? Did I do this in a, why did I do it like that? Sorry. Okay. That made no sense. So this is, well, that also made no sense. So this is phi equals 0 to phi equals theta. So this should also be changed. So this is from 0 to theta d phi of, and in the z hat direction, z hat doesn't change with the integral. I just wrote it over there because it makes it look less cluttered. This integral, when you have just the d phi in the integral is phi, and so you just evaluate it at the endpoints. This whole thing just equals theta. So you get that b2 is equal to mu naught I over 2 times theta over 2 pi in the z hat direction. So that is the result that we are interested in. The theta over 2 pi is the proportion of the circle that's included in the wire segment. So this is true for any choice of theta, pretty much. Maybe there's something that happens at close to 2 pi, but this seems to work. And hopefully that was very useful to you guys. I will see you around.